Yeah, so my name is Ignacio, and I gave Peter a very vague title for my topic, but after actually thinking about what I'm going to be saying today, I gave it something more specific to the talk. So it's going to be Gaussian process for map uncertainty modeling in underwater SLAM. And as usual, I'm going to start with a quick intro to the keywords here, which are basically SLAM, uncertainty, and Gaussian processes. And then I'm going to move on to my actual research and what I've been doing for the last few months. So a quick introduction, as usual. So what's underwater SLAM, what we want to do, and how we do it. And I've said this many times already, so I'm going to go very quickly over it. Basically, so we have an area under the seabed that we want to map, right? We want to build some kind of 3D reconstruction that helps us navigate it, and we have an AUV whose position in space, and over time we can more or less track through the reckoning system. So let's assume that we know where the vehicle is more or less at every point in time. And then we have some kind of sensor, in this case, multi-beam echo sounder, that gives us some kind of 3D coordinates with respect to the vehicle position of the area of the seabed that we're looking into, right? So far, so good. So maybe I can move those. Cool. So we put those two things together, and we basically have a map of the area we want to survey, right? And that's the theory, but the truth is that that's not how it works, because we have cumulative error on the vehicle positioning from our dead reckoning, right? So the farther we travel, the more the error, and then the more uncertain the vehicle will be of where it actually is, and well, the worse our data will become. And same happens for the multi-beam echo sounder, the kind of sonar we're using here. It works well, but we need to be close enough to the bottom to actually get good resolution reconstructions, and it's very noisy. So that means that you can't always trust it. And when you put those actual two things together, then our maps eventually look pretty bad. Now, that is why we need SLAM, right? So yeah, that's the need, SLAM. And SLAM, the simultaneous localization and mapping problem, is a family of solutions for this kind of issue. Given a survey where we collect some vehicle pose and some sonar or some 3D reconstruction of the environment based on the vehicle pose, we put those two things together and we try to come up with an approximation that maximizes the consistency of the map and minimizes the error across the system. Basically, we want to have an estimate of the vehicle trajectory that is as close enough as the actual vehicle to the vehicle trajectory as possible, and we want to have a map that looks as close as possible to the real map. Now the problem is we're working underwater and we don't know what the real map looks like. By the way, I'm going to put a timer because yeah, can you give me a 5 minutes time or something? Nice, thanks. Yes, yes. So because yeah, I was talking about these errors that we have in SLAM, and is there any way we can model these errors, this cumulative drift error and this noise in the sensors? And the answer is, of course, yes. We apply noise models to our sensors. We apply some kind of filtering or optimization techniques to the AUV pose estimate, and so we end up with this fully probabilistic approach, which is SLAM, which helps us optimize all this noise within the system. Right now, that works well, and SLAM kind of works. But problem is our output is still a vehicle trajectory and a map, and the map doesn't tell us anything about this uncertainty in our system, right? So when I look at this map, it doesn't tell me, I mean, it's obviously wrong, right? Because these three should be together. But when I look at it, I don't know which one of them must be more accurate than the others, because one of them was collected at the beginning when the vehicle was still not so lost, right? So we want, but I don't know, if I've never seen where this comes from, I don't know if that is this or this or this. So the question is there any way, and this is a specific question I'm doing my research on, is there any way that I can take all this uncertainty from my SLAM solution, this, I don't know if this goes here or here with this kind of range, and can I put it on my map? So when I look at my map, I know, okay, this area is actually really good because the vehicle wasn't very lost here. But, you know, after 3 rounds, this area is not to trust because the vehicle was entirely lost there. And again, just by looking at a point cloud like this, I do not know, right? And I cannot go there and check because this is under the water and there's no structure that I can compare and so on. So this is my research question. Can we represent and utilize that uncertainty from the SLAM solution in our map? So that's not only me when I look at the map, but when a vehicle looks at this map and tries to use it for localization, for example, the vehicle can say, okay, I shouldn't trust this area, or I should, and so thing is, a good looking map is useless unless it is correct, but we don't know if it is correct because we don't have ground truth. We don't have structures under the seabed that could help us usually realize if the map is good or not. So if I use a drone to build a 3D reconstruction of this building, and I look at the reconstruction, and I don't look at the building, well, if there is a wall here and then half the wall here, I usually know that that 3D reconstruction isn't good because I know that walls usually go together, right? But when I look at rocks and hills and yeah, all this relief, I don't know. It all looks good enough to me, right? So we don't have that ground truth. That's why this uncertainty in our maps is particularly important in underwater SLAM, as opposed to things that we can actually see. So yeah, my point is, when I look at my map, I want to know where the vehicle was, how lost the vehicle was when collecting it. And so I want to have that area of my map with some kind of higher uncertainty measure, right? And we'll talk about what that uncertainty looks like in a moment. Yes, so we cannot do that with usual point clouds or meshes, but we can do it with Gaussian process. Yay. So what is a Gaussian process? I'm going to try to explain it without actually saying what a Gaussian process is, because it's heavy. So I'm going to give you an applied introduction based on the underwater reconstruction. Big sentence. So Gaussian process is a machine learning technique that helps us model distribution over functions. And that doesn't mean much, but if I give you an example, then you probably understand. In this case, the function that we want to model is the 3D bed, right? It's a 3D function. So just by imagine that this is just a usual 3D chart, and our function here is just a seabed that we're trying to map. And this is a machine learning technique, so we need input training data in order to learn this 3D function. And our 3D data, in this case, our training data is the multi-beam beams. So now imagine that we cut this and we paste it here, and that's what we're looking at here. Now imagine this is our prior on the seabed. So we have a big area that we have not mapped. We don't know what it looks like. It could be that it looks like this. It could be that it looks like this. It could be that it looks like any function that we can kind of evaluate in this range. And this is our uncertainty, right? When we get a data point here, it could actually be, this uncertainty means that even though I got my point here, it could be here, or it could be here with more or less the same probability. So this Gaussian process is empty, it's untrained. Now we start to collect measurements, multi-beam pings, 3 points, right? We start to place them around here. And as we do, and we train the Gaussian process, it starts to constrain all those possible functions, right? The range of all those possible functions, so they go through our data points. So now that I know that I have a multi-beam beam here, I know that there is ground there, right? And so my Gaussian process knows that my terrain is going to look like this in this area, and then like this, and then like this, and so on, right? And where I don't have multi-beam beams, like here, I have higher uncertainty, but much smaller than now, because I know that whatever my terrain is between those 2 points, it's not going to be like this. Well, it's unlikely, might be, but shouldn't be. So it's going to be something like this or like this, and so on. So basically, what happens in between this and this is the training of these GPs, and we do it with our multi-beam data. And that is Gaussian processes with our Gaussian process. More questions later. But yes, so what does the Gaussian process after the training give us? It gives us a continuous representation of the seabed as opposed to a point cloud where we will only have these samples, right? Now we have a continuous function. So it's filling up the holes in between our missing data. It gives us it smooths out the noise. So because of certain assumptions you take when you design your GP, as I said, you wouldn't have a point like this, because I'm assuming when I train my GP that this is not happening. So it's going to smooth out all that noise. So if I have a multi-beam here that is noisy and that is obviously wrong, the GP will just throw it away. It's a super cool thing. As opposed to a point cloud where you have to store 1 million 3D point clouds to build a map, this is just an equation. It's basically a mean and a covariance matrix. So, and it's SMaRC, well, not this one, but The ones I'm going to talk about are sparse, meaning you don't need to store 1 million points anymore. You can now store a much smaller number of points, so that it's very easy to carry that map. And in an AUV, obviously that's good because we don't have a lot of memory and we want to map very large areas, right? So GPs are cool for that. And as I said, it models the uncertainty, which was the goal here. And that's what you could look like, what you will see here, right? That's my uncertainty. I know very well what my map looks like here. I don't know so much here. I'm very uncertain here, but the GP gives us that. Holy shit, really? All right. Yes, so I'm using a flavor of Gaussian processes called Stochastic Variational GPS. And this is what the result looks like. This is my point cloud. This is the GP after training. Basically, the closer, the better. And this is the variance. This is the uncertainty of my map, right? This is telling me yellow, I don't know what's here, normal, because I don't have data. Dark blue means I have a lot of data there. It's good, I know what's happening. Why am I using stochastic variational Gaussian processes? Because they can manage very large areas. They can handle the uncertain inputs, which is what I want. And they use inducing points, meaning they are sparse, well, as I just said. They can represent very large areas with very little data. You sure it was 15 minutes? I started late. Yes. Okay. What was I saying here? Yeah, right. It's not going both ways. Yes. So as I said, inducing points, thanks to the fact that they are sparse, I can map very large areas with very few points. I can learn those inducing points. And a very cool thing about SVGP is that those inducing points, when I learn my GP, they gather around the areas on the map that are interesting, right? So if my map is very flat, there won't be inducing points there. But if I have a hill here and another hill here, the inducing points will cluster around those areas. And those are the areas that I'm interested in when I want to localize or run SLAM, because those are the areas that I can use as landmarks. Like, hey, I've seen this rock before. And yeah, those areas will not only be clustered with inducing points, but they will also have lower uncertainty because of this. Keep running. Yes, so this is some examples of clustering on the maps you've seen before. And basically what you see on these small clusters with colors is that, again, so some black magic of GPS, these clusters are being created naturally when training the GPS, such that they gather around the areas with big hills, with big landmarks. So the GPS are giving me the perfect landmarks on my map that I can use directly for active localization. I had a cool video, but because of Joanna, you're not going to see it. So, I mean, yeah, maybe you do. Wouldn't be fair to put it on you, but this will be an example of right. I mean, I might lose my last 3 minutes on this. So, yeah, well, this was an example of active localization with a particle filter using those inducing points clusters. So basically, yeah, we're gonna just go through it because I don't have time. Basically, now when I run localization with a particle filter, as you've seen some time ago, I can do it on those GP maps, and I can use those inducing clusters as active landmarks. So my vehicle with a backseat driver can decide, okay, I have to go from point A to point B, but as I get there, my uncertainty is growing over a certain threshold. So I'm gonna find the closest cluster next to me. I'm gonna go there, I'm gonna relocalize and decrease my uncertainty, and I'm gonna keep going. So at the end of the day, we have a mission with a lower uncertainty and an AUB that, damn it, there we go, that knows very well what it is. Yes. It doesn't get bigger again. All right. Second point of my research, full propagation of the SLAM uncertainty onto the GP. As I said before, we have all these uncertainty sources on the SLAM framework, right? I don't know where my vehicle is. I don't know where my sensor is actually giving me the point. Can I take all those uncertainties from my SLAM solution, which are represented in the covariance matrix, and can I feed them to the GP so that it can be trained with it? And the answer is yes, with a little bit of work. Using some specific SLAM techniques, something called Isam, I can do this in a very efficient way. I can sample this gigantic covariance matrix, take only the pieces that I like, and use it on the SVG training, so that at the end of the day, I got all my SLAM uncertainty here, where I can see it and where my vehicle can use it directly. Questions later, please. And this could be, this is very early research, so it's not looking great yet, but this is just an example of the whole pipeline. I have an AUV going around, running SLAM, collecting some data. I build a graph. That would be my ground truth against my, because of simulation, against my dead reckoning. I optimize the graph, and I use that covariance metrics from my SLAM posterior to train my SVGP with every uncertainty in the system being fed into the SVGP, right? Results, well, intuitively, the result is going to look worse than the map that I had before, but that is actually good because I don't want maps that look good. I want maps that represent reality well, right? And so if my vehicle was very lost when collecting this map, I want to see a blurry area there. I don't want to see a beautiful piece of seabed that is just off. I want to see an area that looks blurry because the vehicle was lost. That's how you can use it. And this image is actually wrong. The colors are inverted, but they look alike more or less. 2 minutes. Right, last piece of research. A raw black ice particle filter SLAM approach with SVGPs. It is a work with a master student. Why RBPF SLAM as opposed to graph SLAM that you've just seen? Because we don't need to match stones when we run RBPF filters. When we run graph SLAM, as I just talked about landmarks, right? I need to see, okay, this rock and this one, I've seen it before. It's the same. I can run SLAM. We don't need to do that explicitly with RBPF. It just, let's say, it does its magic and it runs SLAM for us. So I'm just going to show you the cool pictures. Yes, same, good handling memory. So we run some rounds on simulation. Small bathymetric survey like this. We collected some multi-beam pings. And yes, and this is what a GP looks like on the real life. So we are training, we're collecting multi-beams and we're feeding them to the GP as we go. And so what you see, right, on top, real data, GP, mean, GP variance. And as the AV moves and collects new data, it grows. Oh, I'm running out of air. Yes. And then that's a cool thing. Something I haven't mentioned about GP, I mentioned GPs can infer, they can guess what the data, what your area looks like in between data points, right? So you have a sample here and here, but not here. But the GP is going to give you an estimate of what things look like in between. And that is very cool because it helps you fill the gaps. If you see here, our raw data looks like this. We don't know what's here or here, but the GP is already giving you an estimate of, yeah, I think it's going to look like this, and it's going to look like this. And as you can see in the variance, it is higher on those areas because the GP is not entirely sure of, okay, I don't have data here. I can tell you an estimate, but it's going to have a high uncertainty. And that is good because it's something we can use directly. And so we finish the mission, we have a cool map, and RBPF SLAM as a SLAM system not only gives you a nice map, but it also gives you a vehicle trajectory. And that's what you see here. So the black, which you don't see, but it's down here, that's the actual vehicle trajectory. Red is the dead reckoning estimate. Green is the RBPF solution. And as you can see, once we close the loop, the vehicle corrects and gets back to top of the actual, the filter corrects and gets back on top of the actual vehicle post, which you see here on the error and covariance uncertainty of filter. Goes up, but look closer. Error goes to 0, certainty goes to 0. Wow, future research. I was guessing I will be out of time already. So we'll leave it for another day. Thank you.